I'm sharing my screen right now, and I should be looking at there. All right, good morning, everyone. You haven't seen me in the morning session for a year, so you might be seeing it right now. Today's topic is extending OPCDI to the field level, including TSN and 5G. I am Alexander Gogolev. I am representing here OPC Foundation Networking Work Group of the Field Level Communication Group, and I work for Huawei in a German research center as a research lead. And to get rid of some uncertainty about the terms, I would like to iterate once again. FLC is the field level communication, and it's a group. And it's a group and it's an initiative where technical working groups consisting of volunteers of the aforementioned companies work on developing the solution. The solution is called FX, the Field Exchange. It's a standard, and it's the product of the FLC, and it uses the extensions of all kinds of OPC framework to meet the diverse requirements of the field level communication, specifically so controller to controller and controller to device. If we look at that, and clearly you would need that to be used in factory automation, motion control, instrumentation, safety, you name it. It says here that we're mapping to existing standards, but it would be more precise to say that we're reusing the existing standards and we're based our work in FLC to create the UAFX as a standard and as a solution, reusing as much as possible that there existed. And of course, it first of all spans back into OPC and as well into IEEE. So IEEE 802 specifically, and a collaboration between IIC and IEEE 6802, which is called Industrial Standard for Time-Sensitive Network, Time-Sensitive Network for Industrial Automation. Also, including the GPP, which will be later on mentioned in a few slides, including 5G. Let's go further. So if we are to look at the layered stack architecture of the OPCDI, we will see that there's already quite a lot of stuff that has been developed before. There is application level, there's device models, there is base models, there's communication patterns, there's communication security, there's communication connection establishment, a lot of other things. And on the network layer, so if we are referring to the OSI model, on the layers 3 and then below that, we have things that are specified before us and for us in various guises. We are just going to be reusing some of them, specifying what specifically are we going to use from those standards, and we will go into TSN specifically, layer 3 QoS if we need that, and some other things and features. Some of those will need to be developed. So if we are talking about OPCDI FX and converged networking, which is something that tends to be neglected, it's very important that UFX actually, when one of the key driving moments for UFX development in FLC has been designated as convergence. And convergence here specifically means OPC UFX is designed in a way that it will interoperably, I wouldn't say amend, but it would like complement any other automation system that is using the same transport. Because, for instance, currently the only mature technology that we can use is TSN, is specifically in 6802 guys, and it provides a lot of mechanisms. We're using parts of those mechanisms in certain way to guarantee that we can have deterministic data exchange and make sure that we are not disturbing anybody else on the system, on the network, and so on and so forth. And when we're talking about controller to controller, controller to device, and we're talking about system, and we're talking about solution development, which is something that I need to highlight, it's a little bit different from 6802 because this is the question we often get asked is, okay, there is IEEE, they know what they're doing. They have created together with IIC this 6802, and it specifies TSN for industrial automation. Why do we need UAFX? And the simple yet not the full answer would be, okay, we are specifying a middleware to enable devices to work with each other, to controllers to work with each other. We're specifying certain concepts that didn't exist before, that later on being found valuable by some other standardization bodies as well. What's more important, I would say the definition here is that IEEE and IEC have created a standard specifying the also reasonably rich TSN mechanism set for industrial automation, saying like, okay, for industrial automation, you may not need this, you may not need this, but you certainly need this, and you have to use it this in a certain way. And if you need determinism, you should use it like this, and you should specify these things and these things. What UAFX does on top of that, it adds the solution part. We are not just saying, oh, we would like this to work somehow. We actually explain what's necessary for a device to be good enough using not just TSN, but also UAFX. If it's a device, if you are creating a device, if you are a device vendor, or if you're a device user, you would know how to bootstrap it. You would know how to set up security. You would know how to use the diagnostics. It will be in almost every device. We're talking about, I mean, certain subsets will be in every device. We tend to drive our decisions by small and large scale installations. We heavily discuss required use cases and not required use cases. And in certain times, we specify things that are absolutely necessary, but we leave the vendors room to decide whether they're going to use our specified mechanism or the existing mechanism. So in certain ways, OPCDI specifies the outcome of a standard, not the follow through. So not the procedure, but the outcome. So in certain ways, in certain bits and pieces, for instance, with DHCP, we mandate certain support, but we don't mandate all devices to use it. We leave the room for freedom for the vendors and the customers to decide which one they use, because not everybody needs it. DHCP setup if they just use 3 devices and 1 controller. We look then into interoperability. We benchmark it with performance. We are talking about the future with CUC and CNC, which is the central user configuration, set network configuration for the whole system. And of course, we discussed engineering, commissioning, and decommissioning of the device, of the controller, and the whole system. So this UAFX as a result will be more of a description of a system that works, not just a standard that designates a certain part of the device and so on. So that taken out of the picture, let's talk about the actual topic of the today. Let's dive a little bit into the transport architecture. And on that picture, you can see that there is multiple things that already exist and in OPC UA. And one thing that I would like to right away get out of on the table, so to say, is the OPC UA client server using TCP/IP. This is something that has existed long before the FLC has started working on field level communication. But we know that OPC UA client server, as good as it could be in certain cases, it's not very efficient for small data chunks. And there is quite some protocol overhead, and it's also not really that real time. I mean, real time and non-real time is something that we can debate. Certain latencies could be achieved with client server, and has been shown to be done this way. And there's nothing wrong with that. You could, if you need. However, in OPC UAFX, client server is only used to set up the POP-sub-based UAFX connection. So an OPC UA POP-sub is using UADP, the specific format of UDP, of encoding for field level communication. Yeah, and this can be transported over TSN, over 5G, over regular Ethernet as well. No problem with that. However, the difference between client server here is that client server is a stateful connection. If it's broken, it's broken. You have to reestablish it. With POP-sub, it's a stateless connection. The device just publishes data on the network and then hopes that the network has been configured to take care of the delivery. It's like giving up your parcel to the postman who shows up and say, okay, I got the address, I've written everything else, now it's off my hands. Or driving yourself to the address of the delivery and delivering your parcel from hand to hand yourself. And currently in UAFX, with all that POP-sub and statelessness and everything else, we mandate OPC UA POP-sub over UDP/IP. So I will say in a few slides later why we do this. This is due to the fact that we are striving for interoperability in this first step. We option a few other things that allow for much higher performance in terms of latencies and everything. But currently we only mandate POP-sub over UDP/IP. The most efficient way, clearly, would be to insert the OPC UA data or directed or encoded and wrapped in UADP directly into Ethernet frames. This is also allowed. This is also specified, but it's not mandatory in UAFX. So when you work with UAFX, if you turn off all the security and you use Wireshark and you look at the wire, you will see the data being transported and it can be readable and so on and so forth. Then you turn the security on and nobody can read anything, obviously. Currently, we have specified the networking facets, and we specified them already and released that for bridge and the end station. Specifically for the bridge, end station is still needs some work. And this is where I would be talking the most of the presentation, I guess. As you can see on the picture, on the bottom side, we have the bridge-related connectivity features being nested in a facet manner. We have a base facet, we have an advanced facet, and we have the full facet. So bottom left, and you can see the base facet, advanced, and the full facet. These are the bridge facets, right? So we define 3 facets. I will go deeper in the next slide. What specific features do they have? And every next facet includes the previous facet as a subset. We have done that in comparison with 6082 that just has conformance class A and conformance class B. So 6082 defines 2 profiles, so to say, for low performance devices, so to say, and high performance devices. So clearly not all devices need all the latency capabilities, all the determinism capabilities that the TSN can offer. And clearly all those features being implemented cost money. And yeah, it's just logical that we specify certain devices that are less capable and specify certain devices that are more capable. However, in FLC, we have found out that it doesn't work with 2 profiles because certain QoS features are difficult to be put in either low or high performance profiles, so to say. This is why we have the 3 facets. And the base facet, in terms of QoS, includes VLAN and remote management. So if you know what Ethernet is, you would know what kind of latency it can guarantee you for 1 hop on certain link speed. Worst case, best case scenario. Then we have the advanced facet, which adds to the base facet the frame preemption, and with a small chunk of 64 bytes, and it adds a time sink. Also, if you know your Ethernet, if you know your speed of the link and everything else, you already know which per hop latency in store and forward mode your bridge will be able to deliver. Therefore, your network becomes completely deterministic. You already know what you need to do where. And then we have the full facet where we add to the previous ones, we've added scheduling, which is called time-aware shaping nowadays, or enhancement for scheduled traffic. That's what the IEEE calls it, or QBV. That's the standard name from a couple of years ago. And that specifies the determinism even further. There you have fully scheduled transmissions, and the whole network is completely real time, or I could even say hard real time, I guess. And you can't get more deterministic than that using Ethernet. So performance-wise, there's been papers published, and I think up to this date, this is still the best existing transport in terms of determinism. Though some vendors may argue with me on that regard. Why did we do it this way, and how's that relating to the IP and UDP IP that we actually mandate? I mean, this is the bridge, which is layer 2, and IP is layer 3, and we also actually mandate UDP, which is above that. Well, there is a reason for that. So once we mandate UDP, we say that UDP uses IP. And once we use IP, we are kind of interoperable throughout the network because everybody knows IPv4 and everybody knows what the content of whatever data frame on the wire means. The direct layer 2 mapping and support of TSN feature currently in UAFX is optional, so you don't have to do the super fancy layer 2 mapping and data transport and whatnot. You can, but you don't have to. And with that combination of UDP, IP, and mandatory base facet for bridge and stations, we provide the graceful degradation of quality of service, which means that all of the devices connected will be interoperable, whether they support base bridge facet, advanced facet, full facet, or no facet at all if they're not bridged, if the devices don't have a bridge or something like that. they will still be interoperable on IP level. And that look like this. If we break down the actual facets, you will see that the base facet on the right side, we have the TIX options for mandatory features and O for optional features. And if we go on the left side, you can see the column with all the abbreviated, so to say, QoS features that are necessary or mandatory now in UEFX. You will see that the base facet basically contains the strict priority in terms of QoS and 8 VLANs and 4 hardware queues per port. And then certain buffer lengths and 8 queues in hardware and engineered time clock. I think it's a clock thingy. Is optional, and advanced profile makes all that mandatory, adds a few features on top, which is preemption with non-final fragment size of 64 bytes, and GPTP or .1AS in that particular case. We could say that, I guess. Mandatory and add optional per stream filtering and polishing, and also you can have optional scheduling. However, even in the full, you can see that per stream filtering and polishing is optional, and but scheduling is mandatory. And we also introduced a mandatory depth of the schedule of 16 lines per 100 megabit and 64 lines for 1 gigabit data link speed. And we still have the optional lengths of buffers and optional extended lengths of the schedules. And what would that look like if we were to connect a system like that? And here is the colorful picture that tries to explain that. Here we have the blue box on the upper left corner. This is the UEFX base facet, which means that all the devices here, they support at least a UEFX base bridge facet, which means just the strict priority and the 4 hardware queues in terms of QoS guarantees on the network. And we have the yellow box on the bottom left side. This is UEFX advanced bridge facet, which adds to the base facet frame preemption and time synchronization. And on the right-hand side, we have a kind of greenish box where all devices, controllers, and devices support FX full bridge facet, which means they can do time scheduling, preemption, strict priority. They have 8 queues, all of that stuff, time synchronization, and so on. In addition to that box on the bottom right side, we have an advanced device and a base device, and we have a gray device. A gray device is the same device as on the upper right corner of the picture. This is brownfield hardware or unmanaged switches or something else that is there that you're not aware whether it can be managed, what kind of QoS capacity it does have. So this is the part of the robot cell or a special segment of your plant or factory network that you're not aware whether you can guarantee any determinism with that. So if you were to make work with these 4 boxes and between them, you will see that it actually gracefully degrades, right? So it's pretty clear that within the green box, all the devices can do the UEFX full bridge facet QoS capabilities, which means they can have the highest determinism between each other, and they're happy doing that. However, whenever they need to talk to segments of the network that are less capable, the QoS that is there degrades exactly to the level that is there. So if the green box on the bottom right, green segment on the bottom right needs to talk to the yellow segment on the bottom left, the overall resulting QoS guarantees while they're talking to each other will degrade to the yellow. If the green box on the bottom right needs to talk to the blue box on the upper left, then it will degrade to the base, right? And the same if the same green, very capable segment of the network needs to communicate with the gray segment of the network where nothing can be guaranteed, everything degrades to the gray. Yet all of the devices still are capable of talking to each other. It's just the guarantees are not going to be there, and you will know exactly where they're changing. You will know exactly where they're existing or not. And yeah, this way the network or the system can be built in a way that yeah, a graceful degradation of the QoS is possible. All right, let me talk a little bit more about the TSN in OPC UAFX. Oh, okay, here we are. The key building blocks here are as envisioned for the future, and by standards, IEEE and IC the 6802. The plan is that you have certain controllers, like on the bottom left side. You have certain devices, you have certain bridges, and you have something with embedded bridge on the bottom right side. And you have the user configuration, which is the CUC, the abbreviation that has been around for a few years now. And you have the network configuration, which is CNC, central network configuration. This is the case for a centralized configuration of the network. Well, what's important here is that whenever a device, a controller or a device needs to communicate to another device, the plan is that it communicates to the central user configuration, which in its turn communicates to central network configuration, then uses netconf to communicate to the bridges and back to the device, whether this communication that the device has planned for itself is possible. This is great, and you can do that with certain quality service. It could be frame preemption, it could be schedule traffic. You can just use strict priority, and if that suffices your use case, this is just fine. A bit of confusion typically arises with CUC and CNC, and let me clear this up. CNC is a central network configuration. This is not specified with any UAFX. This is not specified by vendors. This is specified by the standard by IEEE, and I hope that 6082 will further enhance the use cases for the CNC, but it's TSN specific. In this particular case, central network configuration is TSN specific. There's going to be, if we're talking about central network configuration in general, because there's hybrid model, there's distributed model. We're not talking about them yet because we haven't worked them out yet, but in a centralized use case, the network configuration is TSN specific. So if you have a whole TSN network and you have not just UAFX devices working on that network, you will still have one TSN central network configuration. However, you will have a UAFX specific central user configuration, and you may have an additional central user configuration that is not UAFX specific. For instance, you will be using, I don't know, I'm not sure if I can call names, but another vendor widely known solution on top of the TSN. I have heard there is Profinet over TSN. There might be something else over TSN, CC-Link TSN, something like that. They may provide an additional central user configuration for their own specific proprietary technology, and those configuration entities will coexist on the network, and they will both talk to the central network configuration for TSN. And that will ensure that whatever the requirements from different devices, from different parts of the network, even driven by different middlewares, will be still satisfied in the way that the network is not disturbed, because the network is controlled or managed by the central network configuration CNC over netconf, talking to the bridges, and making sure that the network is not messed up by just some devices deciding to do something of their own. Right, so if we are going to talk a little bit about how the devices are set up and how this whole thing is actually working, well, currently, and we're talking about the solution approach here, you still have to have the engineering tool, and you'll probably have to have an engineering tool anyway, because a lot of the factory, and if not all of them forever, going to be engineered. Where a device and engineering tool, so basically you have your engineering tool. Currently it's going to be UAFX specific, but not necessarily standard and open. It could be a vendor engineering tool, I guess. It reads the device descriptor, device offline descriptor from the device, and it says like, okay, I know what the device is, and you can configure it using your tool and push that configuration back to the device. So that's what we can see on the left side of the picture when the engineering tool is talking to the controller. Then the same device configuration will be submitted, not the same, some parts of that will be submitted to the user configuration, because not all of the device configuration has to do with communication, right? So commissioning a device is a bit more complicated than just communication. So all of the configuration goes to the device, the communication part goes to the user configuration, And that will in order say, okay, my device will be needing to publish certain data at certain speeds, at certain amounts, at certain times. Dear network configuration, please provide me this. And network configuration will talk to all of the bridges in the system and say, okay, if you want to publish this data here and you want it to be delivered there, we can guarantee you the corridors. We can make sure that your data is delivered on time. And UFX specific stuff is resolved with CUC. TSN specific stuff is resolved with CNC, and that should magically work out. And those switches, they will, of course, use all of the features specified in 6082 and further specified in UEFX to ensure the determinism of the data exchange. Now, coming to the 5G, we've been talking a lot about TSN. Well, 5G is newer to the game. It has been actively marketed as URLLC. Some of you may remember that. Started around 2016, 2017 as well, which I think results to ultra reliable low latency communication. And 5G has been showing that it can do certain millisecond range communications. And the question was, why don't we do the automation with that? And it's wireless, it has a lot of inherent benefits. And what would we use to run over that network? Because 5G is basically a network, and it's actually an IP network. I think since UMTS, it's all IP based, or since 4G, it's all IP based. And of course, they reached out to UFX and we started talking, and I was part of those discussions. And the discussion started as 5G network. We're being represented as a one TSN bridge. What kind of guarantees could be provided? How these guarantees could be modeled? How can we use them? How can any of that be connected? What does CNC do here? What does the CUC do here? How these concepts could be merged, or whether they should be merged at all. QoS mapping, as you may imagine, wireless networks have very different concepts of QoS and delivery guarantees than the wired networks, because you don't control the media. There's a lot more unknowns in the communication. What shall we do with the time sync? Because for highest determinism and data exchange in automation, you need very tight time sync. And what about redundancy? If certain channels fail, the data needs to be delivered. How do we unify the orchestration between 5G and TSN, and how all of that will work with UAFX? Well, there's been a few approaches to that. The work is ongoing, I have to say that still. There's been some meetings, there's been some discussions. Actually, last year, I think we published, well, when I say we, it's 5G ACIA, so it's not exactly we as me, but I was part of the discussion, and we have, I think, cleared up quite a few important items and differences between the 5G and the TSN as the transport. And I want to stress that once again, UAFX is agnostic of the transport. It actually is not connected to TSN, and you can run your UAFX even over regular unmanaged bridges. You're just not going to get the most deterministic data exchange. If you use unmanaged switches and regular Ethernet, any network event can disturb your communication. TSN is just a way of ensuring that your data is getting delivered from A to B, nothing else. But UAFX is agnostic of that, and we specify certain things to work with any communication technology underneath layer 2 or layer 3 in that particular case. We had been discussing this to reach the guaranteed bandwidth and bound latency, and I think certain concepts made it into the latest white paper of the 5G ACIA, and to be discussed in 3GPP. Standardization process there is sophisticated, and I think we will have more to report in the close future. Currently, I think there is sufficient demos that can show you that certain communication can happen deterministically and reliably over the wireless media using 5G and using UFX. And my company, Huawei, in this particular case, has been a member of the demo wall for UFX with our 5G 1 millisecond installation since a few years now. You can see it on most of the major automation fairs around Europe, at least. All right. All right, to conclude my lengthy presentation, TSN, and specifically TSN specified by IC IEEE 682, enables determinism and network convergence that OPC UAFX is using, but not limited to. Currently, FLC is preparing the integration of 6082 into OPC UAFX, and I have to say that saying we are preparing for integration is another statement. We have a lot of things that are just completely interchangeable. We're referencing whatever we can and just reusing whatever the terms are. It just so happened that there's a lot of things that you need to standardize, and there's a lot of discussions, and there is a lot of reasons why certain things have been discussed over many, many months and even years. And 6082 has been closing now on the first release, and we're waiting for that. And once it's done, we will cement that in our specification as well. C2C release is a best step we had, and it enables really the plug and produce TSN. It enables communication, not just controller to controller, but controller to compute, controller to cloud, really. There is another initiative, cloud-specific communication in OPC UA, has been just started. This will be interoperable most likely with C2C as well. 5G integration and alignment is ongoing, and there is some progress, but it still needs some time. So till we get there and see the bright world with wireless and deterministic communication in automation plans, we still need to get some time into that. All right, I think that would be it for me. Let's see. Yep, that would be it. OPC UAFX control to controller demos, everything. You can see them in Europe, you can see them in Americas, you can see them in the Eastern Hemisphere as well. Thank you very much for your attention. If you have any questions, just connect to me on LinkedIn, ask me a question. I'll be happy to help. If you prefer email, just write me an email. That's also, or to anybody in FLC, that's also encouraged. Thank you very much, and goodbye.